In this lecture, we begin looking at molecular compounds. Now, the massive variety of these molecules makes it necessary to add a layer of complexity to the nomenclature. And don't worry if you have to come back to this lecture a few times. I do. Let's look at the non-conductive molecular compounds. Now, these compounds don't produce ions when dropped in solution, since they're bound together by the sharing of electrons. These systems usually have no metal elements. There's a wonderfully massive variety of these compounds, and there exists the possibility of very complex structures. There's a whole year of chemistry to just characterize the huge variety of carbon, hydrogen, oxygen, and nitrogen-containing compounds called organic chemistry, and the nomenclature rules can fill multiple pages. Now, we're going to keep it simple at this stage and just concentrate on naming binary, two-element compounds for now. But be aware, we are barely scratching the surface of these types of compounds in their somewhat more complicated nomenclature. For ionic compounds, the ordering of the atoms in the molecular formula is relatively simple. Cations, metals mostly, are written first, and the anions second. The ordering of the elements in chemical formula for the molecular compounds is not as straightforward. What if you had a molecular compound containing one nitrogen and one oxygen? Would the ordering be NO, no, or ON, on? Well, the general rule is that the more metallic elements are listed first. These are main group elements found more to the left and down in the periodic table, and they are closer to the actual metals on the periodic table. They are also known as electropositive elements. For simple systems, the following list guides us with the elements on the left side of the list written in the molecular formula before the elements on the right side of the list. So, the answer to our NO or ON formula for a single nitrogen and single oxygen would be NO. Here are some of the different molecular formulae for a variety of nitrogen-oxygen compounds: NO, N2O, and N2O3. Now, having names that can distinguish between all these different compounds is the reason nomenclature rules are critical in chemistry. First, we will establish common prefix names that represent the subscripts in the molecular formula for these types of compounds. These prefixes are in the table on this slide and should become familiar to us. We will demonstrate how to use these prefixes and the nomenclature rules for these types of molecules by naming the N2O3 compound first. We look for a prefix from the table that represents the number of atoms of the element that is listed first in the molecular formula. We have 2 nitrogens, so the prefix is di. We then find the prefix for the number of atoms of the element listed second in the molecular formula. In addition to the prefix placed on this second element, we tag on an "ide" suffix. Using this basic naming scheme, the name of the compound N2O3 would be dinitrogen trioxide. In this naming convention, we also have a couple more naming rules that are applied in special circumstances. The mono prefix is omitted if it applies to the first element. So for the compound NO, we would say nitrogen, not mononitrogen. When the prefix of an element in the formula has an A or O at the end, and the element also starts with a vowel, so that 2 vowels are adjacent to one another, the A or the O on the end of the prefix of the element is dropped. For example, instead of saying monooxide or nonooxide, we eliminate the last vowel of the prefix and we would call these elements monoxide or nonoxide. That being said, the I at the end of a prefix on the element in the formula, such as di or tri, is never dropped. So the name for our NO compound would be nitrogen monoxide, and for N2O, the name would be dinitrogen monoxide. Everything seems to be working out, except there are many compounds which, when out of the water, are considered molecular compounds and don't have metals in their formulae. But when placed in water, the water tears them apart, ions form, and the water solution conducts electricity. Now, a great many of these particular compounds are known as acids and bases. The great Swedish scientist Svante Arrhenius, one of the founders of the branch of chemistry we know as physical chemistry, in 1884 gave us an initial definition of acid and base compounds in water. Arrhenius defined a base as a compound that creates OH- hydroxide polyatomic ions in water, and an acid is a compound that produces an abundance of the polyatomic H3O+ hydronium ion in water. Now, we don't want to get into the nitty-gritty of this acid-base chemical process yet, but you can see why these types of substances would complicate things for scientists who are trying to categorize different compounds. Out of the water, they look like molecular compounds, but in the water, they become ionic, just like metal-containing compounds. Let's take ammonia, NH3, as our first example. This compound, when dissolved in water, can transform into two polyatomic ions, the hydroxide ion, OH-, and the NH4+ ammonium ion. Now, ammonia is a base by the Arrhenius definition here, because of the abundance of the OH- ion now present in the water. This result is so common for ammonia that we sometimes rename the compound when in water ammonium hydroxide. Wow. The compound is ammonia when not in water, but ammonium hydroxide in water. It's confusing, but also informative as to the kind of chemistry we're doing, acid-base chemistry. The culprit in all of this confusion is the hydrogen, that pesky, hard-to-categorize element on the periodic table. For now, let's concentrate on just trying to name acids. We already know how to name something like LiH, lithium hydride, because this is considered a type 1 ionic compound of a metal with the H- hydride anion. But things change when we have hydride compounds with nonmetals. The following table is the IUPAC names of hydrides of the main group elements, which we would consider to be molecular compounds. In the table, the name in the parentheses is the common names of these compounds. The columns in the table represent groups with numbers identical to those on the periodic table. Now first, I would not expect to know all of these. I dare say most science students don't know the details of the IUPAC naming of the hydrides. You can test this out by going up to a chemistry major and asking them for the IUPAC name for water. I know I don't remember that it's oxidane. Many will say dihydrogen oxide, but they would be rigorously incorrect, even though they are following the binary rules in naming the compound. The same goes for ammonia, which has an official IUPAC name of azane. Naming ammonia trihydrogen nitride is also, well, not correct. Now the acids in the group 17 column marked red in bold, you do need to know because they are common chemicals in most laboratories. These are called the binary acids. Now obviously when these compounds are in water, they turn the water acidic and will make the water conduct electricity. Many of the polyatomic ions containing oxygen atoms can contain hydrogen. For example, the carbonate ion CO3 2- can become charge neutral with the addition of two hydrogen cations, giving us the molecular formula H2CO3. The hydrogens, strictly speaking, are bonded in a molecular, not ionic way in this compound, but H2CO3 in water makes the water acidic, so the formal name for this compound is carbonic acid. These oxygen-containing polyatomic acids are also called oxoacids. Now, we don't have to put two hydrogen cations on the carbonate ion. We can put just one hydrogen cation on it, producing a new polyatomic ion, HCO3-, which we call hydrogen carbonate. The common name for this polyatomic ion is called bicarbonate. The nomenclature for the neutral compound, sodium HCO3, follows our rules for metals with polyatomic ions and has the IUPAC name of sodium hydrogen carbonate. The common name is sodium bicarbonate or sodium bicarb if you're extremely lazy, like an actor on TV playing a doctor. Hey, nurse, give me some sodium bicarb, stat! The most common of these acids and the polyatomic ions they produce are in the following table and should become familiar to us. The common names are in parentheses. For the acid names, it's clear that if the ion has an ate suffix, the acid form will have an ic suffix. These are marked red on the table. If the ion, though, has an ite suffix, the acid will have an us suffix, marked in blue on the table. Obviously, ionic and molecular compounds can get even more complicated and will stretch the nomenclature rules to the limit. And folks, we haven't even gotten into the other types of compounds like metallic and coordination compounds. But don't worry, the nomenclature described in these last two lectures will be sufficient for most of the chemicals that we'll see at the introductory level. Till next time.